At this point, we have two ways of finding approximate solutions to equations. One is what I'm going to call the subdivision method, which I'll remind you about how this works in just a second. The subdivision method just requires that the function you're working with be continuous. And we also have Newton's method. And Newton's method requires that the function you're working with be not only continuous, but actually differentiable. So the subdivision requires less, the subdivision method requires less of your function. But what I want to do is compare how quickly these two methods zero in on the exact value of the solution to the equation that you're actually looking for. For the example for this, I'm going to use one that's pretty easy to compute Newton's method for, just to make it easier on us. And also, I'm going to use one where we actually have some idea of what the exact value of the solution is. So we're going to solve 0 equals x squared minus 2. We know that x is plus or minus the square root of 2, right? And we're going to start with x sub 0 equals 1, and so we can expect that both of these methods for approximation will get close to the positive square root of 2, because the positive square root of 2 is about 1.4. In fact, let me write out many, many digits of the positive square root of 2, just so we can see, as we're doing this, how each of these methods is doing. So 1.414213562373. Okay. Of course, the square root of 2 is irrational, so this decimal approximation never starts repeating. It's always changing. Okay, so let's work out the subdivision method. Now, how the subdivision method works is, first you have to start with some interval where you know there is a solution. Or, I guess more specifically, you have to start with an interval. So we're looking for where the function f of x is x squared minus 2. We're looking for a place where this function is 0, because that will be a solution to this equation. So for the subdivision method, you have to start with an interval where this function is positive at one end of the interval and negative at the other end of the interval. And going from 1 to 2, well, if we plug x equals 1 into this function, we get, so f of 1 is minus 1, so it's negative here, f is negative here, and if we evaluate this function at 2, we get plus 2, so it's positive here. Right, so since this function is continuous, and it's negative at one end of this interval and positive at the other end, it has to be going through 0 somewhere on this interval. That's the intermediate value theorem for continuous functions. So the interval we're going to start with is from 1 to 2. So the approximate value, what we're going to do is subdivide this interval, and we're just going to cut it in half. So in the middle we have 3 halves. So the x value for this stage is 3 halves. Now we need to know whether our function is positive or negative at this x value. So we have to compute f of 3 halves. So that's 3 halves squared minus 2. 3 halves squared is 9 quarters, which is a little bit bigger than 2. So 9 quarters minus 2 is positive. Okay, so our function is positive at this midpoint. All right, so now our interval, right? Remember, we're looking for an interval where the function changes sign, so that's the interval from 1 to 3 halves, not the interval from 3 halves to 2. Since there's no sign change on this interval, we're excluding this interval. So now we know that there has to be, this function has to have a 0, a root, somewhere between 1 and 3 halves. Okay. Oh, notice that 3 halves is 1.5, right? So 1.5, we don't have any digit. We only have the 1's digit correct. All right, so for our next stage, our interval is from 1 to 3 halves, so the midpoint of that is 1 1/4, so 1.25. I'm going to start using decimals now just so that we can more easily compare our results to the the decimal approximation for the square root of 2 up here. So 1.25, so we need to take 1.25, plug it into our function, so square it, and then subtract 2, and we get negative 0.4375, and that's less than 0, so right, negative here. So now we can exclude this interval, so 1.25 is in here. So now we know that there is a solution between 1.25 and 1.5. Okay, so now we take the midpoint of these two, which is 1.375, I guess. Is that right? I think that's right, 1.375. And evaluate the function at this x value. So 1.375, square that, subtract 2, and we get negative 0.109 and change. So that's negative. So again, so negative here. So we throw away the left interval and keep the right interval. So now our interval is from 1.375 up to 1.5. So something that you might notice is that we still don't have this tenths digit correct after several stages of this subdivision method. So the next value that we would try is, I guess, always the midpoint of that interval. So 1.375 plus 1.5, all divided by 2. So 1.4375. Now we need to evaluate the function at that spot. So square it, and then subtract 2, and we get 0.066, so that's positive. So now we're going to throw away the positive here, so throw away the right interval, keep the left interval. So now our interval is 1.375 up to 1.4375. All right, and the midpoint of this interval, so 1.375 plus 1.4375 divided by 2, 1.40625. So I'm going to stop here after, let's see, 1, 2, 3, 4. I guess this is our first round, right? This was our starting value. So our first round of computation was here. So 1, 2, 3. After 4 rounds of computation, we have, so this is the fourth stage, we have 2 digits correct for the square root of 2. So, you know, this subdivision method, on the one hand, it's sort of conceptually very simple, right? All you're looking for is you're subdividing an interval and then looking for the subinterval where the sign of the function changes. But it appears to be kind of slow. It's only very slowly inching towards the exact value of the square root of 2. So now let's try this with Newton's method. So for Newton's method, we have the function. We need the derivative of this function, which is 2x. So let's start out with x equals 1. Right? So this is our first stage, second stage, third stage, fourth stage. Let's see, 3, 4. So I guess maybe we should call this our 0th stage. First, second, third, fourth. And just to make it fair, let's go to the fourth stage for Newton's method. So for Newton's method, for the second stage, right, we're going to use the formula for Newton's method. So you take the previous stage minus, and then plug this one into the function. So we get 1 squared minus 2 over, and then take it and plug it into the derivative. So over 2 times 1. So 1 minus, let's see, minus 1 over 2. So 1 minus negative 1/2, that's 1.5, so 1.5. Okay, so after one step, well, we don't have a great approximation, but remember, it takes Newton's method a step or two to really get rolling. So for our next stage, we're going to take 1.5 and plug it into Newton's method. So 1.5 minus 1.5 squared minus 2 over 2 times 1.5. Okay, so calculator time. 1.5 minus 1.5 squared minus 2 divided by 1.5 times 2 is 3. I messed something up when I entered that into my calculator. Let me try that again. 1.5 minus, open paren, 1.5 squared minus 2, close paren, divided by 3. Okay, that's better. 1.416666. These sixes go on forever. All right, so you can see after 2 stages, we already have 1.41. Right? So already after 2 stages, Newton's method is doing better than the subdivision method did after 4 stages. All right, so let's save that. And let's compute step 3. So I'm going to stop writing down the formula and just do the computation. So our previous x value minus our previous x value squared minus 2 divided by 2 times our previous x value. Uh-oh, I think I made a mistake. I definitely made a mistake. Let me get our previous x value, store that. Okay, so previous x value minus our previous x value squared minus 2 divided by 2 times our previous x value. I get 1.41421 and change. And you can see actually we already have this correct out to here. So maybe I need to write down more decimal values. 41421.5. Okay, that one finally is different. 5, 6, and so on. So now let's store that and do one more step of Newton's method. So previous x value minus previous x value squared minus 2 divided by 2 times previous x value. And this time I get 1.41421356237.5. So where's our first incorrect digit? Looks like after 4 steps, Newton's method gets this correct out to the very last digit that my calculator even keeps track of. So all of these digits are correct after only 4 steps. Now, if you've ever programmed a computer to do anything, you can imagine that programming a computer to do Newton's method is actually going to be a pretty straightforward loop. Right? You just program in the formula for Newton's method and ask the computer to repeat it. So a computer is going to be able to flash through 4 rounds of Newton's method in no time at all. And that gives us an approximate solution that is incredibly accurate. Very, very accurate. In fact, I mean, how do you think the calculator came up with this decimal approximation in the first place? It did some sort of numerical process very similar to Newton's method. Maybe not exactly Newton's method, but closely related. That's actually how computers come up with these decimal values. They use these numerical processes, and often it's Newton's method. So the point of this is that the subdivision method, although it is conceptually simple, it's so slow that it's actually garbage. Newton's method is really the best way to find approximate solutions to equations and get incredible accuracy with only a modest amount of computation.